Hello, welcome everybody to this monthly webinar of TriboNet. It's kind of a tradition. First of all, thanks for joining. I see a lot of familiar names, so yeah, thanks for coming again. Today, well, we can wait a couple of minutes, but today we have with us, besides Eider, we have our guest, Steve Franklin, which is already here and listening to you. As usual, well, you know the drill. Steve will amuse us with his presentation about tribology for engineering design. And any question, any doubt, any clarification, just write it on the chat. And later on, we will go through them. If time allows, we will also ask you, or if the question is a bit complex, we will ask you to unmute yourself so you can just talk to Steve directly. So as dynamic as possible. With that, please, Steve, you have the spotlight. Whenever you want.
Okay, good. Thank you. I'm not sure you can't see me in the camera yet. I guess at the moment, or can
we
you?
Can. We can.
You can. Okay, good. I can't see myself in the camera. Okay, so but so this afternoon, I'd like to talk to you about tribology for engineering design, or designing for lifetime performance. As Xavier mentioned, I have a number of positions which I'll talk about. I'll show you a slide about that. Amongst other things, I have my own consultancy business to help people with tribology in engineering and also in research. But so what I'd like to talk about this afternoon is, first of all, I'll go briefly through my background. And for those of you who are not familiar with the word tribology, I'll briefly explain what that's all about, and how to analyze a tribological case. And then I'll go through a number of case studies, and depending on the time, it will either be 2 or 3 case studies. So this talk is mainly aimed at practicing design engineers in industry, if you like, but I think it will be equally interesting for academic people listening and watching. And my background is really very varied, and it's been I like to call it a career on the edge, if you like, on the edge between industrial research and development and academic research. I've always sort of been somewhere in the grey area in between there in my career. I'll go through my background briefly then. So first of all, I have a bachelor's in applied physics and materials science, and I got that from Sheffield in the UK. I did a PhD also in the UK in Loughborough, University of Loughborough. And then straight after that PhD, I went to the Netherlands, which is where I've lived ever since 1986. And I worked for Philips for a very long time. And there at Philips, Philips is a large company, of course, you've heard of it. And there I worked on a number of different areas. So performance and application of tribological coatings and surface treatments, and then more broadly on friction and lifetime performance in product and machine design of all sorts of machines and all sorts of products of Philips. And I also worked a lot on biotribology, which is more about how products like shavers, like toothbrushes, like catheters, interact with the human body. And this was also related to tribology. Following that, in 2007, I started my consultancy business, the Franklin Consultancy, and I also worked for 4 years as a senior principal architect at ASML, on another big company that makes machines that make the semiconductor chips. And I also worked at as a research. I took over a research group leader position at ARCNL. That is a Dutch research institute. ARCNL stands for the Advanced Research Center for Nanolithography. So basically, there they do a lot of the more fundamental research for ASML nanolithography machines. And my group then focused on friction and wear behavior in relation to that. And that is now, the group leader is now Bart Weber, and he was previously my postdoc in the group when I started, and then he is now taken over the group leadership of that group, because people get old, like me, I get old, and then you have to give these things to younger people. So since 2008, I've actually also been a visiting professor in tribology at the University of Sheffield in the UK. So I go over to Sheffield every few weeks to help some PhD students out with giving some direction to their research and some staff as well. And I do the same since the beginning of this year at the University of Amsterdam. And just to show that I haven't been completely as in the industrial research and development, but I also do a lot of academic research, and I've published more than 60 publications in scientific journals, and I also have about 17 patents. So this is just an overview a brief overview of my background. What I'd like to start off this, the main part of this lecture is what is tribology. So tribology you may have heard of, you may not have heard of it, but it's all about friction, wear, and lubrication, where friction is simply a force, a tangential force between two surfaces that are moving and in contact. Whereas wear is about the loss of material from the surface, or displacement of that material on the surface and damaging the surface. So there are friction and wear do completely different things, but they do influence each other. And I always see lubrication really as a means of influencing or controlling friction and wear. Friction and wear are typically characterized by the friction coefficient, which is the normal friction force divided by the normal force on the surface. And the wear is normally characterized typically by something called the specific wear rate, sometimes given the symbol K, which is the wear volume divided by the normal force times the sliding distance in sliding wear. And just to say straight away that these two characteristics, the friction coefficient and the specific wear rate, are certainly not material properties. A lot of people think they are, but they're certainly not. They're often time dependent because the surface changes, and over time things happen on the surface, and that means that these friction and wear are time dependent, and they're very much dependent on the local surface conditions. So we normally talk about a tribological system, which is two components in contact with each other, moving with respect to each other. There may or may not be some sort of lubricant in between there, or it could also be water, and all of that is encased within an environment of some sort, which may be air or maybe vacuum in space applications, for example. So all of that make up the tribological system. And really, when we talk about tribology or friction and wear, we have to talk about those as characteristics of the whole system, the whole tribological system. And friction and wear, you can see from the definitions there, are most certainly surface phenomena. So anything that happens on the surface or changes on the surface changes the friction and wear behavior. So tribology is really everywhere. It's part of everyday life, and it's very essential to the functioning of all sorts of products and machine systems, as well as you can find it everywhere within nature. But the basic principles and the mechanisms involved in tribology often remain the same. So friction is about the tangential forces, as I said. They arise from surface adhesion phenomena. They may arise from abrasive ploughing or interlocking, for example, between roughness asperities interlocking with each other on the surfaces. It may arise from a non-perfect elastic behavior, so viscoelasticity, where you lose some energy during the displacement process of one surface on another. And wear, loss or displacement of a material, that can arise from a number of different mechanisms or phenomena, like adhesive transfer of material from one surface to another, abrasive ploughing, or surface fatigue, or some sort of tribochemical reactions. A number of different mechanisms that can go on there. And you can find all of these mechanisms and phenomena occurring in different applications, very widely different applications. But the basic principles and mechanisms often remain the same, and only the relative importances of those principles and mechanisms differ from case to case. So what does tribology mean in industry? So, tribologists talk about friction, the force resisting motion, and wear, loss of material from the surface. But in industry, the word tribology is relatively unknown, and people talk more about things like lifetime performance and reliability, because that's important for the guarantee that companies have to give to their customers for their product, or it's important for the reputation of the company, or sometimes liability. They talk about maintenance, because that's important for the downtime of machines or productivity. It can be also important because in certain applications it's very difficult to carry out maintenance. Think, for example, about wind turbines in the North Sea, very inaccessible, and it's rather difficult then to carry out maintenance. So these sorts of things are the concerns of industry, and they have a number, and you can explain why they're important for industry. But you don't see the words friction and wear or tribology carrying on here, appearing there. So, in other words, tribology means different things in industry, and you often need to translate between the industrial and the business needs, which are these things here, listed here, and what is important for tribology research. There's often a translation needed there. If we talk about wear rates and lifetime performance in general, changes in the wear rate. So what I'm showing here is the amount of wear expressed in a volume of material that's lost from a surface as a function of time. And what we can see is there is a maximum for any product or application. There's a maximum allowed amount of wear. For example, there's a maximum clearance that's allowed for the application, or tolerances specified for the application, and that represents a maximum amount of wear that can take place for that particular application and that particular component or product. So this is this dotted line here that I'm indicating. And that maximum cannot be exceeded within the required lifetime of that product or application. So then you have a minimum required lifetime, the dotted line here. And if all goes well, then the process of wear over time doesn't exceed this maximum allowed wear within the minimum required lifetime. And we can see we have three distinct parts to this wear rate. So first of all, we have a relatively high wear rate, which represents what we call running in wear. And then if all goes well, that goes into a steady state area where you have a much lower wear rate over time. And then finally, something happens and it fails, sometimes catastrophically, and the wear rate shoots up again after a certain time. Hopefully that occurs after the minimum required lifetime has occurred. But what could go wrong is that that running in wear can just simply carry on and you don't go over into the steady state area. It carries on, and we call that severe wear. It can happen that the steady state wear rate is simply too high, where we exceed this maximum allowed wear too soon before the minimum required lifetime is achieved, or some sort of early catastrophic failure can occur too early, like some sort of surface fatigue behavior, which causes failure. That also means that the maximum allowed wear is exceeded too quickly. So how can we influence all of that? How is the tribological performance influenced, and how can we point towards some solution directions? Well, if you think of tribological performance in the middle here, then we can influence that by a number of types of solution directions, and those are in, first of all, in mechanical design. So we can talk about bearings and gear system principles, contact geometries to influence the contact mechanics at the contact between two surfaces. We can use elastic elements, or we can use some tricks like side slip to reduce friction reduction, or vibration to reduce friction reduction. Those will influence the tribological performance. We can also look at the materials and the surfaces. So of course there's lots of different materials to choose from, some of which will be appropriate and some of which will not be appropriate for a particular application. We can talk about coatings and surface treatments, because as I said, friction and wear are surface phenomena. So if you put coatings and surface treatments on the surface, then you're going to directly influence the friction and wear straight away. So that's possible. We can also look at surface texture and roughness, also a big influence. And then thirdly, we can look at the lubrication area, so both the types of lubricants and also the lubrication principles to influence the tribological performance. And these three interact with each other, and hopefully to find solutions. A fourth area that also very much influences the tribological performance is, of course, all the application conditions, requirements, and the constraints of the application, like what sort of loads and speeds are going on, what is the type of motion that is occurring, the temperature, the operating environment, what is the lifetime specification, etc. And these are things in particular that may be fixed by the application and not possible to change, some of which some can and some cannot be changed in order to influence the tribological performance. So this is sort of like a generic solution space, if you like, for how to deal and how to influence the tribological performance. So how do we analyze all of that? So first of all, it's important to look at the functional and the lifetime requirements. What level of design is required? Are we talking about designing something from scratch? Are we talking about designing or evolving an existing design and making it better? Or are we talking about troubleshooting a failure that from a particular design of a particular product or machine that has failed in the field or at the customer, and trying to troubleshoot why that has failed and how to solve that failure? That very much influences, first of all, it influences the constraints that you have. So troubleshooting a field failure and finding a solution, we can't use solutions that are just simply not possible to implement in field, and that's different to designing things from scratch, where you're much more, you have a lot more freedom to choose materials and to choose particular mechanical designs. So this is important to get information about. What is the required function? So what does this thing, product or machine, what does it need to do? What is important and what is not important? What happens if it goes wrong? What impacts does that have? And I say that because in some cases, if it's a healthcare device, for example, and it goes wrong, then that can have much more far-reaching consequences than something that is not related to healthcare, for example. How is the lifetime performance defined, or the reliability defined? Is that in terms of time, or is it in terms of a distance, a rolling distance or a sliding distance? And what limitations are there on the friction and wear behavior? So is it necessary to specify maximum or minimum friction forces or friction coefficients, or is there a maximum allowable wear within the required lifetime? What limitations are there? And then secondly, what the derived information that's always important if you want to analyze a tribological case are things like the type of mechanical contact. What is the geometry of that contact? Is it a simple ball on a flat, for example, as in a lot of tribological tests in the laboratory? Or is it a more complicated mechanical contact? Is the roller can have different geometries of a particular contact? The type of motion, is the motion repeated over the same surface, or do you always see fresh material when you're rubbing, for example, over a product? An example of that is in the machining of metals or other materials. So the machining tool always sees fresh material. It doesn't, the wear is occurring on the tool surface, and that wear is the result of the rubbing always on fresh material. It doesn't sort of rub over the same surface each time. It sees fresh material all the time. And in other cases, in a lot of bearing applications, then you're repeatedly moving over the same area. And this is important in connection with transfer of material from one surface to another, whether that's important or not. Formation of tribofilms on one surface or the other surface or both surfaces. And these all affect the friction and the wear behavior. Load and speed requirements, obviously, are important. Whether there are materials, specific materials that need to be used in a particular application, or particular hardness requirements, roughness requirements, and lastly, but certainly not the least, is the environment. So in what sort of, we're talking about in an air environment, how humid is the air, may affect materials that are particularly sensitive to humidity. For example, is it in water, is it salt water, is it vacuum, or temperature is important. Particles, any particles in the environment are important, as they may cause abrasion. And of course, any lubricants there. And last, not least, what is the freedom to change things? So which of the above are really fixed in an application? And I mean really sort of 100%, they have to be fixed, and which could be modified if necessary. So all of this is needed when analyzing a new case as regards wear and friction. By the way, if you have questions, then you can put them in the chat, and we'll try to leave some time at the end for that we can deal with some of those questions. So feel free to put some questions in the chat. We'll look at them later. So then I'd like to go through a couple of case studies. First of all, a case study that involved a failure analysis and troubleshooting for flexible handling system. So this was a failure analysis. This is something that failed in the field and needed to be analyzed, and needed to find a solution for the field situation. But I'll handle it as if it's more of as if you're trying to design something from the start. I'll explain a bit more in a minute. So what this was about, a bearing system for transportation of heavy products around the factory. So you can see these transportation robots, if you like, that are moving around the factory, carrying heavy products, and they have a bearing system at along this rail here. It wasn't actually a car factory, I'll have to say. But it's about transport of heavy products around the factory. So what we have here are some steel rollers with 26 millimeters by 500 millimeters So it's a roller with a larger radius in one direction than the other direction. That means it's an elliptical contact area. These steel rollers are pre-stressed to give them less vibration when you're rolling along the steel strip that they are rolling along. And this is a carbon steel strip with quite a high hardness, 500 Vickers hard. And this steel strip is in purple here on the diagram is fixed by butting or hammering in certain areas to an aluminium alloy beam, which is the main carrier of the weight. And because this is not sort of fixed completely, but just hammered in certain places, butted in certain places, that means that some small amount of slip is a possibility between the steel strip and the aluminium alloy beam. So we have a total normal force of 4.5 kilonewtons. So that's 2 kilonewtons pre-stress and 2.5 kilonewtons load on the products that are being carried. And the required lifetime of this is about 5 years, which is equivalent to about 30 million load cycles of rolling back and forth over the steel strip. And the question is here then, or the questions, so which wear and failure mechanisms are likely or possible? How can these be checked and predicted? And which improvements are feasible? So which failure mechanisms are likely? So we could think of 4. One is simply overloading of the contact statically. So if the roller was just simply statically pressed onto the steel strip, then we might get some plastic deformation there, which is called bunneling, whereby you make a dent basically into the steel strip. That force or that stress that's caused in that contact will also go through to the underlying aluminium beam, because aluminium is much softer than the steel, and it could also cause some surface deformation of the underlying aluminium beam, potentially. Thirdly, we could have what's called surface fatigue. And this surface fatigue is when you roll. Usually, you see it with rolling contact. When you roll over a surface, so that there doesn't need to be statically overloaded the surface, but if you roll back and forth over the same surface many times, then you can start to form cracks beneath the surface that then extend towards the surface, and finally you start getting pieces of material that simply loose and fall out of the surface. So that could be a possibility. And fourthly, we could have fretting wear. Fretting between the steel strip and the aluminium alloy beam. As I said, some small amount of microslip is potentially possible in this situation. And fretting is the process by which, in cases where you have a low amplitude oscillation, so a small amount of slip back and forth at a low amplitude, whereby surfaces of metals in particular can become oxidized because any wear particles that are formed because it's only a low amplitude oscillation, it's difficult for those wear particles to exit the contact area, so they stay within the contact area and they get ground down further and further and finally oxidize, become trapped, and they oxidize. And because sides of metals are in almost all cases harder than the metal from which they are formed, then this causes an accelerated amount of wear, which then continues and it just becomes worse and worse. So that's also a possibility. So as I said, this was a failure investigation, but if it was a pre-design, how could we have checked for the possible failure mechanisms? Well, the static contact overloading can be estimated using Hertz contact mechanics calculations, relatively simple. But you'll find on the internet lots of programs where you can do this. I'm sure TriboNet has that also somewhere in their list of tools. Surface deformation of the underlying beam, well, also contact mechanics. If we look at surface fatigue, then we can do some first estimates using some sort of quick and dirty empirical formula, which I'll show in a minute. And fretting wear, well, that's really based on materials knowledge and previous experience, and we can do some analysis to confirm whether or not that has occurred. So first of all, static contact overloading. We have a roller and a steel strip, and this is the data that we need to carry out the Hertz contact mechanics calculation. I'm not going to go through it all. As I said, it's an elliptical contact because we have a roller with a radius much greater in one direction than in the other direction. We have some data about the elastic modulus of the roller and the elastic modulus of the strip and the Poisson constants of those. In this case, they're both steels, they're about the same. And we have some data about the yield stress, or in this case, the proof stress, 0.2% proof stress of the strip, which tells us when the stress is so high that it starts to deform plastically rather than elastically. So in the analysis, it turns out when you do the calculation that you have a mean contact pressure of about 0.8 gigapascals. We have contact dimensions. So this is the dimensions of the actual contact at the interface here of 0.5 millimeter by 3.5 millimeters. And in that case, if the contact dimensions are much less than the dimensions of the strip itself, which is much larger, 30 millimeters, then we can apply the Tresca criterion, as it's called, and that tells us that plastic deformation occurs if the maximum contact pressure is greater than about 1.1 times the proof stress. And we know the proof stress, so to prevent plastic yielding, we need to have a proof stress of greater or equal to 0.1 times the mean contact pressure. And it turns out that, well, the required proof stress is 0.73 gigapascals, and we have a proof stress of 1.2 gigapascals. So in this case, it should be okay. There shouldn't be any static contact overloading. If there were, then we could think about changing the geometry, increasing the radius of the roller, for example, to reduce this mean contact pressure. But in this case, everything seems fine. So the next one is surface fatigue. So there, surface fatigue is, there's a lot published and known about surface fatigue. Quite often, if you really want a very quick and dirty estimate of whether or not it's going to be a problem, in particular, or rather I should say only for steels in this case, then you can use this formula here, and this was also published in some time ago by myself and my colleague Dijkman, Joshua Dijkman at the time, and so this tells us a relationship between the minimum hardness of steel and a constant depending on the lubrication condition. N is the number of cyclic load changes, and P max is the maximum contact stress in the Hertz from the Hertz contact mechanics, and C is another constant which depends on how how pure the steel is, if you like, so how many inclusions there are in the steel and what the coarseness of those inclusions are, because this can, if you have very coarse, sharp, a lot of inclusions in the steel, then this can reduce the fatigue strength of the steel. If you plot those out for the current case, well, we have a current strip hardness of 500 Vickers hardness, and this is the curve which is based on this formula here, and this tells us that we can have a maximum allowable cyclic load of about almost 3.5 kilonewtons. And in fact, actually, we have 4.5 kilonewtons. So this means that this is not good. So the strip hardness is likely to be too low in this case. And it means that the lifetime requirement of 5 years will likely not be met. I say likely all the time because, as I said, this is a very quick and dirty relationship, and surface fatigue is also not easy to predict exactly. So if we wanted it to be okay, then the maximum allowed load for the steel should be about 2.5 to 3,000 newtons, if we include a safety factor in there. So to bring it sort of well below this value here of 3.5 kilonewtons. And in fact, I said it was a failure investigation, and it did fail, and we saw a lot of indications of surface fatigue actually in this case. So these are SEM, scanning electron microscope images of the surface of the strip, where we can see these hits in the surface. So this is called hitting, which is typically the beginning of surface fatigue. In a later stage, that leads to cracking. So we can see these cracks here, and these are usually perpendicular to the rolling direction, which they are in surface fatigue. And then finally, you get whole chunks of material that break out of the surface of the steel strip, as we see here. And this is really catastrophic failure. So how can we improve matters? Well, we can increase the hardness of the steel strip, or we can carry out a surface treatment such as nitriding or carburizing to improve the fatigue behavior and or at the same time increase the hardness. But unfortunately, those were not possible in this case because it was already in the field, and it wasn't possible to replace the steel strip. It was too expensive. nitride carburizing of a steel strip. Well, the strip is simply too long and it couldn't be made into smaller sections that would not deform during the nitride carburizing process. And the only solution that could work was to reduce the bearing pre-stress to a much lower value of 500 newtons, so that we get the final normal force of about 3,000 newtons. Finally, fretting wear. Well, yes, black powder was observed in the contact between the steel strip and the aluminium beam, and that's certainly an indication of the result of fretting, so an oxide. And in fact, when it was analyzed in the electron microscope, the EDX analysis indicated that it was aluminium oxide, so it was coming from the aluminium alloy beam, as you might expect. And I already explained this, I think, the fretting process. And the solution to this sort of problem is to really to separate the surfaces so that they don't come into contact with each other, and at the same time allow that slip to take place without too much tangential force being developed. And so the solution here is just simply to coat the surfaces with a bonded solid lubricant like molybdenum disulfide. In this case, it's a fairly common solid lubricant that can be sprayed on to surfaces, and then you can heat the surface to bind the coating onto the surface, and then put the steel strip back on again, and then the problem also goes away in this case. So I'm just looking at the time. I have 10 minutes left. Xavier, are you still there? Is it a good idea to do a further to go? Sorry?
Please continue. Well, I found it super interesting, so I do not dare to stop you. Please go on.
Okay, I'll do one more case then. And this is a design verification case. So this is where a design has been made. It hasn't yet been implemented, but the idea is to look at, is that design okay, and is it likely that the lifetime requirement will be met in that design? And this is then for the wear lifetime of seals in vacuum pipettes in a pick and place machine. So do I have a slide here? Yeah. So vacuum pipettes in a pick and place machine is a machine which picks up components, electronic components, surface mounted devices, SMDs. It picks them up and then places them on a printed circuit board where they're subsequently soldered in a soldering machine. And this pipette just simply picks up the components by vacuum. So you have a piston within a tube. There's an O-ring which presses against seal, and in this case the seal is made of a material called Rulon, and Rulon is a Teflon, PTFE composite, which is a PTFE that has been reinforced with fibers to make it a bit more wear resistant. So it's a fiber reinforced PTFE composite, commercial material. So should So what's important here, this is about the sliding of this Rulon seal against the tube, and whether or not that is going to meet the lifetime requirements, whether the wear of that Rulon seal, whether it's going to wear too much within the lifetime, or whether it will likely meet the lifetime requirements. And for that we use something I mentioned earlier, the specific wear rate, because we're talking about sliding wear, so we can use this characteristic. Specific wear rate is given by this formula. So this is the volume of the wear times the specific wear rate times the normal force times the sliding distance. And in a design, when we're trying to use this to predict design and to design a product, then we have to calculate the allowed wear volume, but that usually depends not so much on the volume, but on the wear height, which is based on how much the component is allowed to wear within allowed tolerances that are allowed for that particular application. And they may be different for different services, because the two components that are sliding against each other may have different geometries. So here, if we say the wear height is the same for both surfaces, then this volume here, which is allowed, is much smaller allowed wear volume than on this surface, which is much greater. So we have to calculate the allowed value of this K factor, the specific wear rate, for both surfaces A and B, if they are different geometries. And we compare that with known test data, or we carry out tests that allow us to generate some test data. Normally those tests are carried out in the lab, where conditions are different, never exactly simulate the practical conditions in the lab. Obviously you do your best to do that, but it's never exactly the same. So usually, as a safety factor, we say in designing that the allowed K factor should preferably be greater or the same as 10 times the tested K factor. So that's how to use the specific wear rate in designing, and we did that here. Now this is some data about the application. In this case, the vacuum pipette seals. We measured actually a friction force simply by pulling the piston, and that came to 0.1 newtons. And we know that the friction coefficient of Rulon against the tube is about 0.2. So that from that we can work out what the normal force is, because obviously it's quite difficult to measure the normal force in this case, which we need for the calculation here. We know the geometry of the seal. We know that the seal is allowed to wear by 10 microns on its diameter. And this is in order to maintain sufficient pressure from the O-ring to give a good enough seal against the tube. So if the pressure from the O-ring is not sufficient, then it won't be sealing well enough anymore. And then that gives you a limitation on the amount of wear that's allowed on the seal diameter. So we need a required lifetime of 1 million cycles. You know how much our stroke is, and one cycle is 2 strokes. And we know a K value from laboratory tests 5 times 10 to the minus 16. And then we can carry out the calculation to see whether the lifetime requirement can be expected to be met. And so we have to convert the wear, the allowable wear of the diameter of the seal into a allowable wear volume, and we do that. It's a simple geometrical. It looks complicated, but it's just looking at the geometry of the system of the contact there, and we can work out the volume. We find that the allowed wear factor is about 65 times 10 to the minus 16. And we expect from the laboratory tests about 5 times 10 to the minus 16. So in this case, our conclusion is, well, the lifetime requirement is expected to be met because we have a safety factor of at least 13 there, which is more than 10, so that's sufficient. And we expect this design is fine. There shouldn't be any problems with it. So I think I better finish there because we're 3 minutes before 4 now. I do have another case study, which is more of a pre-development design case study about the wristwatches and whether coating can be used to replace liquid lubrication points in high-end watch mechanism component. But I think I'll stop here and oh yeah, I think what I'll go to is.
You are welcome for you can come again any other Friday. So
Yeah.
you're welcome to come back. So.
I'll go to just this last summary slide. So now I've talked about my background, a career on the edge, halfway between industrial and academic research, trying to guide academic research to be useful for industry. So talked about what is tribology and how to analyze a tribological case, and a couple of case studies. So just to summarize, then I think friction and wear is always about surfaces. That's an important thing to remember. So anything on the surfaces or that changes on the surfaces changes the friction and the wear behavior, and that means you can use coatings and surface treatments very effectively in tribology. Wolfgang Pauli, you might have heard this before. He said, "God made solids, but surfaces were the work of the devil." Which is certainly true. My experience. Yeah, the life of a design engineer is not an easy one, I'm afraid. I'm glad I'm not a design engineer, but I'm more of a specialist tribologist. And I don't have to do all the things that a design engineer has to do and know about. But some basic tribology and materials knowledge does go a long way to helping predict where things might be going wrong. So if you still have time, we can still spend some time answering a couple of questions. I don't know whether there are any questions yet. I haven't looked.
Yes,
Thanks a lot.
yes, there are. Yeah, thank you very much, Steve. There are several questions in the chat, so I will just start with the first one. Leon Jacobs, if you're here, you can unmute yourself and ask the question.
Yeah, hello, Steve. Thanks for the nice presentation. It's very well explained. Yeah, I didn't know the term side slip. There was already a comment in the chat that made it clear to me, but I wondered if it's used often in industrial applications to use this way of decreasing the friction.
Yeah, I don't think. Well, to be honest, I think it's not used often enough because it's a very elegant way of reducing friction in a directional sense. So for those of you who never heard the term before, side slip. So basically what you do is if you experience friction if something is moving on the surface, you can see my hands, I'm putting up here. So I'm moving something on the surface. Here we go. On the surface of my hand. And I experience a force, which is trying to stop me moving that on my hand. If you introduce side slip, which is a movement perpendicular to the direction of movement, then what you do is you don't reduce actually the friction. You rotate the vector of the friction force such that in the direction that you're interested in, which is in this case this direction, then the friction in that direction is apparently reduced. So what you're really doing is rotating the vector of the friction force, and you're accommodating the friction that a lot in this direction instead. And I have seen it used in feeding mechanisms for feeding components along chutes into machines. So sort of vibrating chute that is doing this, such that the components don't get stuck within the chute when they're being fed into some sort of machine for processing. So I've seen it being used in that sense. And I've also seen it used in there's some product on the skin when the mover if we want to move it over the skin and it's vibrating in this direction, that can also help reduce the friction and I'm talking about shaving type applications where you're trying to shave in this direction and moving in this direction is reducing the friction there. But I wouldn't do that with a safety blade, but with more of an electric type shaving when you can't damage the skin too easily. So those are just about the only places that I've seen it being used that I can think of.
And the vector of the friction is, of course, let's say the same vector as the speed in both directions. Yeah.
Yes.
So if you have a big speed in the transversal direction, you have relatively little friction in the longitudinal direction.
Yeah.
Thanks.
Okay.
Yeah. So that question was also asked by Tom Connelly, and there were some comments like side slip occurs when one twists the cork when pulling it from the bottle. So it's this example with a wine bottle.
Yeah, that's it. That's exactly yeah. You can call that an industrial application. It's an application, yeah.
But very useful.
And you do it automatically, don't you, when you're opening a wine bottle? Twist it. Yeah.
Maybe we have time for one more question from Matthijs. Matthijs, you can unmute yourself.
Yeah, thank you. Thanks for the presentation. I had one question about slide 19, where you present the quick and dirty lifetime calculation for the roller.
Okay.
And I was wondering if you have the load gauge of, for example, a roller in a bearing where you have an inner raceway and an outer raceway. The roller sees 2 times a load gauge during 1 revolution of the roller. Could you use that formula also for the case I just described?
Yeah, you'd have to apply it to both surfaces, of course, and I don't see why not. But
Yeah,
I
I
did
was
say
wondering
it was a
because
very I did say it was a very. I'm hesitating a little bit because it's a very quick and dirty form, and it's not really meant for designing bearings or anything, which is if you're really designing commercial bearings, for example, then I wouldn't like to use such a approximate method as this. And I'm talking about designing ball bearings or roller bearings or ball bearing company or whatever. You know, they have much more sophisticated methods of estimating the fatigue life of bearings. But this is really a very quick and dirty tool that design engineers can use just to give a very approximate estimation of whether or not they're likely to be in a danger area or not. I would consider it. But I don't know whether that's related to your question or not.
I was thinking of the bearing is just an example of I was wondering about till how far can I use that equation, and you can say maybe, okay, then if the radius of curvature of the inner roller, of the inner raceway or outer raceway is a variable I can use, then maybe you can do a comparative study that you find out that maybe not the exact, you don't calculate the exact lifetime, but you can compare one solution to the other, and then determine which one has the longest lifetime.
Yeah, I see what you mean. The difference in radius between the inner and the outer is not going to be that great, though, is it? Is that? Do I understand you correctly?
My train of thought is that then the Hertzian contact stretch is a function of effective radii, and that's something with outer something with the raceway. Okay, again, you have the raceway radius and you have the roller radius. Together they make an effective radius, and that's also for the outer raceway. So there's some room to play. And that
they're not.
The
they're not going to be that much
makes
different.
Okay, because in the formula,
unless we're talking about very big, very, very large diameter rollers, of course, but there's not going to be an enormous difference, I think. Yeah.
Okay.
But maybe a good thing here is that actually maybe you can use this in that, as Matthijs mentions, that you can use it as a qualitative judgment. So if you change something, if for example you don't know anything about this, and then you have some parameters to change, and then you change something, you at least know, okay, is it going to make it better or worse?
Yeah, I can see. I think it should be worth using it in that way, assuming nothing else is changing. Yeah, so I think you can. If you look at that, I don't know whether you made a note of the. Well, this is being recorded, so you can look back at it. But I gave a reference there as well for that, where there's some more information is given about that formula and where it comes from. So maybe you can use that maybe you can use that effectively. I hope.
Okay. Thank you. I will definitely have a look at it. Thanks.
Okay.
I think I guess we can stop for today because it's Friday. People going to weekend already. I see in the comments, but and
Yeah.
going to put to practice this side sleep knowledge with the wine bottles today. Apparently, I see. Yeah. So yeah.
So,
Okay, well, there are a couple more questions, but maybe we're running out of time, as Either suggests. But please, well, I know that Steve is very reachable. If you can check the chat, Steve, and if we could post it.
yeah, I've seen a couple of other
uh,
pictures. I'll see if I can answer a couple of the other
Okay. Cool.
the other questions in the chat. Yeah.
Uh,
Okay. Good.
Good. Well, with that, I think we close this session. Steve, you are very popular, and yeah, many people followed. I mean, I think it's the longest webinar that we had, but it was totally worth it. So thanks for that, and thanks everyone for joining us once more. What else? I'd like to, just thank you, Steve, for joining us, Steve Franklin. You got the email there, easy to reach. And just to close, I want to remind all of you that there's like a conference starting this year about tribology called Tribology of the Low Countries, which are the lower countries, sorry. It is in Enschede and it's in April, 18th and 19th of April. They, as far as I know, they want to make it a tradition or some kind of I think it should be annual. So just to, it's difficult to find because they are not, they say they are not too active online, but it's going to happen. April, Enschede.
Enschede, but Enschede close to Amsterdam. So it's Netherlands for those who doesn't know. So.
And the Netherlands.
Yeah.
So, well, thanks for everything and have a good one. Enjoy the weekend. A lot of side sleep. Oh.
Yes.
Thank you, Steve.
Bye-bye.
Yeah. Bye-bye.